Okay. So good. I would like to urge all of you to take the extragalactic course. Look to see if you have time in your schedule, or if it's part of your major. It'll also be a welcome change from our very theoretical course. Okay. So we have seen that if you have a dipole, the potential due to a dipole is given by what? P, yeah, dot r hat over r squared. This is due to a perfect dipole. Okay, so what we're going to do today is we're going to enter into material science. So imagine non-conductors. So imagine, I don't mean for a material to be uniform or something like that. There could be many things going on in a solid material. These are called dielectrics. Okay? They're made up of molecules. Sometimes the molecules could have polarization, like water, for example. It doesn't have to be a solid, but we won't worry about the complexities of a fluid changing shape and so on and so forth. Okay, but there's nothing that at the moment tells you that it has to be solid. If that's the case, for example, you could have these dipole moments, and just randomly pointing. Each molecule has its own dipole moment. And then you submit this to an electric field. If the electric field is not very strong, these molecules are not necessarily flying off, right? But it can easily rotate. There's a torque. The torque on a dipole, recall, is P cross E. So immediately, the dipole is going to start rotating. It'll rotate until what? When is the torque 0? Zero, right? I mean, even if it's exactly opposite, that also works. But that's not very stable. The slight thing, and it's going to do this. So what's going to happen the moment you turn on the electric field? Yeah? Now, all of a sudden, the dipoles are going to align. So this is sort of before, and this is after. When I say before and after, in this context, what does that mean? Before and after what?
The electric field.
Before and after the electric field was turned on. Now, suppose you have not necessarily a polarized material. So again, let me do it this way. This is before. Okay. I'll sort of divide before and after. And all of a sudden, you have, you slowly turn on the electric field. Now what's going to happen? In every molecule, the positive charges feel a force in the direction of the electric field. The negative electron cloud feels an average force in the direction opposing the electric field. As a result, what's going to happen? You're going to have this sort of a positive, negative charge separation. So if you have a molecule, and don't get me wrong, so the next one is also separate, right? So all of these molecules are going to separate, and then again, once again, the song remains the same. These dipoles get aligned to the direction of the electric field. Now, all dipoles, all materials are not necessarily so nice, so perfect. This doesn't happen all the time. But this is a good place to have this conversation going, getting started. Okay? And we'll talk about its complexities, how it changes, and so on and so forth. And we know that a single dipole, let me use this very clearly. I'm going to denote that by a p, a small p. Okay? And now we're going to have a bunch of dipoles, regardless of how they were formed. So at any point, I cannot talk about the polarization I can, but the polarization at a point in a certain region, in a certain average region, I can think of as an uppercase P, which is polar. It's too bad that we use the same letter P. They're totally different. This is polarization per unit volume. So I get a detail. Yeah? So if this is true, and if they're actually made up of real dipoles, then now I can write the potential. Look at this, uppercase R prime, denoting, I'll make that clear as well. So wherever there are polarization charges, I can place my coordinate system inside or outside. It doesn't really matter, right? So R prime. And I may be measuring the potential, again, inside or outside. Now I have to use the separation. This is my separation vector. I don't want to use this at the moment. We will. It turns out what we're going to do is actually a lucky guess. Okay? But at the moment, I'm choosing to measure my potential outside, not inside. Why is that? Because this is a dipole approximation formula. It's only true when when R is significantly away. If I take this observation point and keep it inside the material, well, right there, the dipole's located at that particular spot, you cannot use this approximate formula. This came from a dipole approximation. Yeah? The dipole approximation is only true for a perfect dipole, but there's no such thing. Physical dipoles will have higher and higher moments. So to be accurate, we have to measure our potential a little further outside. Okay? A little bit of usual calculus. I'm going to write this as 1 over 4 pi epsilon naught expressions from before. I'll run out of space and I have to erase things. Gradient of this is minus r hat over r squared. I didn't put the minus because I'm taking gradient with respect to the other variable, the primed variable. Because all derivatives, we've talked about this, derivatives, when you take derivative with respect to the primed variable, it becomes negative of that. Okay? Good. So why did we do that? Obviously, we're going to do a little bit of calculus and just shuffle things around. This can be written as what? First term, I'm going to write this as 4 pi epsilon naught divergence of P over separation vector d tau prime minus 1 over 4 pi epsilon naught divergence of P correct? Where did that come from? This term is like that term. So that's equal to this term, the total divergence, minus this term. Yeah? Okay? This is obviously, I can use the divergence theorem here and write this as 1 over 4 pi epsilon naught P dot n dA I'm going to put this plus to bring about a nice little interpretation. Now I know how to interpret this. You have, again, let me do a recall. This is in general, nothing to do with rho of r prime over r d tau prime plus sigma of r prime dA. I feel like this is a bit squished. Correct? All I have to do is compare these two. So then I know if there exists such a vector field as a polarization vector field, I can imagine the whole problem to be solved because of stuff we know already. It's exactly like this if you make the assumption that The polarization surface density is nothing but on the boundary. Yeah? And you see that's why I took the minus n. I just want to identify which one is the. And then it's like physics you've seen already in chapter 2 or something. The polarization charges are not like your typical electrons in a conductor. Electrons in a conductor can run from one side to the other. You just turn on the electric field. That's why they're called conductors. The charges are allowed to move. Here, each molecule is just doing what? When you turn on an electric field, all the positive charges move one way, and the negative charges move one way, and they sort of get a dipole moment. They're not moving around. Because of that, these kind of charges are denoted as and talked about as bound charges. Okay? We'll distinguish them from now on out of charges coming from this sort of an extraction as bound, and your regular old charges, we'll start calling them free. Yeah? So the subscript B is placed. And all we need is the old formula. Now, remember what's happening here is suppose you have a material, you might get this. You get negative, positive, negative, well, they'll be close together because they're just moving apart, right? But if I look in the middle, there is no net charge. The net charge comes how? You see the edge of it. So that is this guy. Now, this is a complicated object. This is saying the polarization vector is not uniform. So it is changing directions and whatnot. Therefore, there could be some charges. And we'll talk about this more and more. But let's do a simple problem to get a sense of how to deal with all of this. Because of this expression, all you need to do is sort of remember this. And then you realize that the formula is the same old. Okay, fine. I'll explain something very soon. I'll say it, it may make sense, and you'll forget it, but you have to revisit either my video or more importantly, Griffith has a nice section. Remember the catch, we have used this polarization dipole formula, which is only an approximation. So we have to use this away, outside the material. In a few minutes, I'll show that this can be used inside the material as well. Nothing happens. But I have to make that argument. It's a very subtle argument. It doesn't help or hurt problem solving. Problem solving, you're just solving a formula. But understanding is, of course, more important. So let's do a simple problem. To do this problem, I'm going to recall a previous solution we did from last chapter, namely example 3.9, because then we can cheat. And as you know, cheating is good. I didn't say that for posterity. So example 3.9, I'm just going to copy down the results. Example 3.9. Here the problem was, and what we did, we solved the Laplace's equation using spherical coordinate system, and then we found a way to solve potential inside and outside. And in this example, a charge density in the boundary is given to you. And using Legendre polynomial, the question is, find the potential both inside and outside. And we did this in general, but of course, if I don't tell you what the charge distribution is, you're not able to calculate the exact potential. So, but we did a specific example as well. Your book did. It's unfortunate that Griffiths picked K. This is not 1 over 4 pi epsilon naught, just any constant times K. In this case, there is an inside potential and outside potential, and I'm just going to copy off. It's an example we did in class, but I shall also very specifically tell you what equation numbers they are. So V inside is K over 3 epsilon naught R cosine theta, and this is coming from equation 3.86, and K R cubed over 3 epsilon naught 1 over R squared cosine theta, and this is 3.87. Now, what is the problem that we are about to do, and how does it help us? What we're going to do is, well, let me state the example so that you know what I'm referring. I mean, the problem number. So it is example 4.2. So obviously, if we're going to compare the previous problem, it's a circular, I mean, it's a spherical object, solid object, except now there's no charge in it, but this is made of a polarized material. And the polarization vector is uniform. So this is P, and this P, remember, it's the polarization per unit volume, right? Is some constant in magnitude, which I'm going to call P, and it's constant. Just a number in the z hat direction. The question itself says find V. Let's begin by finding the bound charge densities. Well, what is divergence of P, you think? It's a constant vector, 0, which is equal to a negative bound volume charge density. There is no charge density inside. Well, it's uniform. You know, all the heads and tails are aligned, so internally the heads cancel the tails, so to speak. But there's sigma bound, which is P dot normal. Of course, the normal direction is R hat. So this is P z hat dot R hat. Indeed, that is P cosine theta, the spherical coordinate system. This, of course, it has completely different origin from the previous problem, the example 3.9, but the effect is the same. Sigma is k cosine theta. So all we have to do is replace k with p. All right, let's do that. That's easy enough. PR cosine theta over 3 epsilon naught. Let's find the electric field. Turns out it's very useful. This is nothing more than z, r cosine theta. So I can write this as pz over 3 epsilon naught. Why did I write it in Cartesian coordinates? A, I can. B, I can easily take the gradient now to find the electric field. Obviously, the electric field is only going to have z component. Well, it's still, or rather I should say E inside is negative gradient of V inside, which is negative P So the inside electric field is against different magnitude because of this 3 epsilon naught points downward. Yeah? This is a very useful result. It's not like a very profound result. It's a very useful result. And let's do V out. That is P r cubed over 3 epsilon naught cosine theta over r squared. What's the total polarization in that sphere? Let's write this answer in terms of the total polarization. Remember, total polarization is that little vector P, right? So P is nothing but big P times the volume, because this is small, or in this case, 4/3 pi r cubed. So then I can write V out as 4/3 pi r cubed times the total polarization. Then I have, what am I doing? I'm solving for P. So that is P over 4/3 pi r cubed. That is this guy. Then I have 1/3 r cubed. I have epsilon naught cosine theta over r squared. A little bit of cancellation. And I get 1/4 pi epsilon naught P cosine theta over r squared. And, oh, not little p, but, I mean not big P, but little p. Which I can now write it as 1/4 pi epsilon naught P dot r hat over r squared. So it's like the outside the sphere, the old formula for the dipole comes out. And inside, it is this curious one. Let me write it. You can take the gradient to find the electric field. It's not very enlightening, but this is very important. Yeah? Yep.
So we said little p was we're saying it's the total, but I thought it was kind of like that instant point earlier.
No, so P is sort of the integrated one, right?
Yeah. Okay.
Yeah.
Okay.
So it's per unit volume.
Yeah.
Yeah. Oh, yeah, correction, when I wrote it, I didn't integrate it. I wrote it like this. That doesn't make sense. It is. Okay, so I'm going to talk about the potential, or hence the field, inside the material. It's a very subtle point. It is not at all complicated mathematically. It looks, in fact, very silly. But it is a subtle point, and we luckily guessed the wrong answer for inside. And that's why it is hard for the point to sink in. So read what Griffiths has to say about it. I'm just going to explain it to you so that you know the story, and you'll forget it constantly, and depending on how much you want to retain it, you should visit it frequently. Again, there's no mathematical difficulty, and that is part of the problem. Sometimes when things become mathematically trivial, you misunderstand. You think you understand. So the macroscopic potential inside the dielectric. Okay. Now remember, the whole thing we're computing with this expression. Right? These are assuming pure dipoles, and we're ignoring all the smaller order terms. This is 1 over r squared, there's 1 over r cubed, r to the 5th, or even r to the 4th, and so on and so forth. We have just ignored them. We have not calculated them at all. Why? We're saying, well, here's a molecule, I'm going to look at it from here. Compared to the molecular size, I'm orders of magnitude away. I don't need to worry about the formula. That is true if you were considering one dipole or a blob of charge. But now what do we want to do? We want to find the field inside the dielectric material. So at some point where you're concerned with, there is a dipole right there. So how do you know what the field is over there? Well, you can't use this formula. Well, you can, but you can't. So that's what I'm going to try to explain. Yeah.
How is this different from that last problem that we just did, where we had our dielectric and we were finding the field inside of it?
No, we just blindly use the formula.
Okay, that was just we have the formula. Now we're actually.
Yeah. So here's my dielectric material, and I want to find out the potential here, or the electric field here. potential slash EF. Electric field is what I mean in this case, that point. So, well, what I'm going to do is I'm going to construct a fictitious little sphere around it. But the sphere is going to be so small. It's going to be very small. Still macroscopic size, just not at the scale of atoms. It'll be, again, atoms, molecules, these are 10 to the minus 9, 10 to the minus 10. Well, I may be 1,000 orders of magnitude away. I may be at 10 to the 6 micrometer, maybe even 10 to the 3rd millimeter. I don't need that level of accuracy. Because for one thing, I don't care about the exact electric field. I couldn't. It's good that I don't care about it because I couldn't. Imagine all the complicated electrons doing its quantum mechanical motion. First of all, these things are not static. Yeah? And when you get infinitely close to an electron, the electric field goes to infinity. 1 over r squared, as r goes to 0, is infinity. But I don't care. All these electrons are moving their motions and they create an average aggregate field. Yeah? That is what I want to measure. So it is not really microscopic, even though it is in the material, I want the aggregate average sort of field. And then I'm going to say that the E field at some point over here is due to two things. Is due to E out plus E in. And I have to explain what is out and what is in. But yeah, I have carved out an empire, so you know who the outsiders are. And similarly, V equals V, let me do it in the same sequence, V out. This is out, this is in. So it's the when I say E out, I mean electric field produced by all the dipoles outside. When I say V out, I mean the potential produced by all the dipoles outside. Obviously, E in and V in means the electric field and the potential produced by these dipoles in my little sphere. So for the outside part, well, I can say this point is far enough from this one. I don't care. So for the outside part, this is good. I'm integrating over all the dipoles outside. V in is what I don't know. But then I get to choose the sphere. I get to decide who's in, who's out. I'm going to pick a sphere small enough. Again, remember, I'm just looking for the macroscopic field. I'm going to pick a region small enough where the polarization vector is uniform. Correct? Because I picked it to be fairly small. Remember, a small enough scale, on an average, everything looks like the simplest case. On one extreme, the Earth looks flat. The other extreme, the dielectric looks uniform. But if it is uniform, we just did the problem before by not paying attention. We used the exact same formula and concluded what? Three epsilon naught. But how did this formula come about? This came about because of sigma bound being P dot N and rho bound is equal to 0. How did this come about? By assuming this is correct. Because thankfully, Martin asked me exactly that question. Well, if you're going to talk about the whole uniform, the field inside, we just did the problem with field inside, but we did that ahead of time. So this is from the inside part. This is from the outside part. But in appearance, what do they look? The same. So the answer to the question is, we don't worry about it at all. And as I'm saying this to you, you're going, yeah, I kind of buy it. The question is, did I talk you into it? I constantly feel like that Griffiths has talked me into it. I have to revisit the argument every single time. This is, in fact, the macroscopic potential inside the dielectric. I want you to reflect over this. Read, I go through every single detail in the book very carefully, but there are certain places where I tell you, read, and reread. Make sure you understand the argument. It doesn't affect our problems at all. So it is, in some sense, good reading because it doesn't, your grade won't depend on it. But this is where, the art of the argument works. And Griffiths excels at this. So read this, make sure the argument makes sense, and come and ask me questions if you need to. Otherwise, we'll continue to plug along.